This first part is about gravitational potential, the gravitational potential energy for every 1 unit of mass. This is measured from an arbitrary reference level like gravitational potential energy. Because it is measured from an arbitrary reference level, physicists spend a lot of time talking about gravitational potential difference, the difference in gravitational potential between any 2 points. You may not have thought much about this topic, but you have interacted with it at times in your life, particularly when you think about the electric batteries or electric cells that energize your portable electric devices. These are rated in terms of voltage. The voltage of a battery doesn't tell you what's in the battery, it doesn't tell you how much energy is in the battery, it doesn't tell you how much power the battery can deliver, but it does tell you something about whether or not the battery can make your device work. And this voltage is what physicists call electrical potential difference. One of the biggest reasons to learn about electrical potential difference is to understand how batteries and cells make devices work. And that's ultimately where we're heading. But first we're going to start talking about a more familiar concept, the gravitational field, and the resulting gravitational potential difference when you move something around in the gravitational field. This is because you don't necessarily interact with electric fields on the same scale as you do gravitational fields. The Earth is a very large mass and we live in its gravitational field every day. Let me set up for a demonstration. Okay, let's think about a ladder in a uniform gravitational field. Each rung of the ladder is at a different level from the ground. When we talk about gravitational potential difference in the Earth's field, we usually would reference the 0 level as being at sea level. But we might just choose this table level to be our 0 level. We can put different objects on different rungs of the ladder. We can put this sphere on the ladder, and by doing so, we raise the gravitational potential energy in the sphere Earth system, and the ladder itself is at a certain level of gravitational potential. I could put a different object on that rung. I could put this book on the rung, and I would have changed the gravitational potential energy of the book object system, but the contribution of the gravitational field of the Earth, the contribution of the ladder, is the same for each object. We can view the different rungs of the ladder as being places where we could store gravitational potential energy of different amounts for different objects with different mass. Obviously, if I use this 4.5 kilogram mass, I'm going to store more energy. But once again, the gravitational potential difference between the 0 level and this rung is the same for the book and the mass. Okay, let's return to our ladder as a useful analogy for gravitational potential in a uniform field. A person climbs a ladder, and with each step they go up the ladder, they store more gravitational potential energy. But once again, there's a contribution of the rung of the ladder and the Earth's gravitational field for each step that we could calculate, and we call that the gravitational potential. If we reference the ladder to the rungs of the ladder to 0 level, say the floor, then we don't need the ladder to think about gravitational potential. It doesn't matter where we put the ladder. We could move it over, or the ladder could not even be there, and we can think about the gravitational potential at different levels with reference to the floor. And so physicists like to think about an equipotential surface that's at this level that represents the gravitational potential at that level. The gravitational potential, symbolized by a capital V, is the gravitational potential energy for every 1 unit of mass. That's symbolized by a capital U over m, and that equals Gy in a uniform field, the product of the field strength and the position. We can keep track of the energy itself, or we could predict how much energy would be stored for a given mass without calculating the energy. An object at a higher level will always store more energy for its particular mass. Near the surface of the Earth, where the gravitational field is uniform, the higher the level, the higher the gravitational potential. In a uniform field, gravitational potential increases as you move upward by an amount equivalent to the gravitational field strength, G. The gravitational potential difference between 2 levels, delta V, equals G delta Y. A way to imagine this idea is to draw isolines of equal gravitational potential. Near the surface of the Earth, they are parallel, equally spaced lines. I'm symbolizing them with dashed lines because they are a representation of the gravitational potential. The gravitational field would do zero work on a mass moved along at one of the gravitational equal potential levels. So if this mass is moved horizontally, it doesn't change its level. That's true even if we move a mass right or left along a higher level. The gravitational field does zero work because gravitational force is everywhere perpendicular to the motion. The gravitational field must be perpendicular to the isolines. If we draw both representations at the same time, we have a picture that illustrates the relationship between gravitational field and gravitational potential near the surface of the Earth. The gravitational field is a vector that has a constant magnitude and direction wherever you measure it. Gravitational potential is a scalar, meaning it has no direction and it increases at a constant rate. Back to our ladder analogy, delta y is the difference in height between rungs and delta v is the difference in gravitational potential between one rung and the next.